Hello everyone, in this video we will see the realization of JK flip-flop using SR flip-flop. So we have studied the flip-flop conversions. So there are 6 steps. So the first step is to identify the given flip-flop and the required flip-flop. So in this question we have to realize JK flip-flop using SR flip-flop. So the given flip-flop is SR flip-flop here, and we have to the required flip-flop is we have to realize JK flip-flop. So the required flip-flop is JK flip-flop. So that is the first step. Now the second step, that is to write the characteristic table of the required flip-flop. So we have to write the characteristic table of JK flip-flop. So the characteristic table of JK flip-flop is, we will be writing Qn plus 1 in terms of Qn, J and K. So that is the characteristic table. So there will be 8 combinations. So JK is the input and Qn is the present state. So we will be writing the next state in terms of present state and J and K inputs. So the combinations at the input are 0, 0, 0, 0, 0, 1. So correspondingly, Qn plus 1 will be equal to, we have seen this characteristic table earlier. So it is 0, 0, 1, 1, 1, 0, 1, 0. Zero, zero, 1, 1, 1, 0, 1, 0. And we all know that for a JK flip-flop, when J is 0 and K is 0, then Qn plus 1 will be equal to Qn. So Qn plus 1 will be equal to Qn, which is 0. When it is 0, 1, the output will be reset. When it is 1, 0, the output will be set, that is output will be 1. When it is 1, 1, then Qn plus 1 will be equal to Qn bar. So here Qn is 0, so Qn bar plus 1 will be 1. And the next case is again 0, 0, so it is the memory. So Qn plus 1 will be again equal to Qn. So Qn is 1, so Qn plus 1 is 1 here. Next 0, 1, it is 0, 1, 0, 1 and 1, 1 again toggle. So here it is 1. So now Qn plus 1 will be equal to 0. This is the characteristic table of JK flip-flop. Now the third step is to write the excitation table of the given flip-flop. So our given flip-flop is SR flip-flop. So now we have to write the excitation table of SR flip-flop. So the excitation table will be writing S and R in terms of present state and next state. So when we know the present state and next state, we can write the input conditions S and R. So 0, 0, 0, 1, 1, 0 and 1, 1. We have seen the excitation table of SR flip-flop earlier. We can copy that over here. So this is the excitation table of SR flip-flop. So it is 0, 1, 0, don't care. From top to bottom it is 0, 1, 0, don't care, and it is 0, 1, 0, don't care. Now we can combine this. The fourth step is to combine the above characteristic table and excitation table to form the conversion table. So now we can combine this characteristic table and excitation table to form the conversion table. So Qn, J, K, Qn plus 1 and S and R. So we have combined these two tables. Now we can write 0, 0, 0. Correspondingly, Qn plus 1 is 0, 0, 1, 1 1 0 1 0. Now we can write S, that is S and R. So corresponding to Qn 0 and Qn plus 1 0, S is 0 and R is don't care. Corresponding to Qn 0 and Qn plus 1 0, again it is 0, don't care. Corresponding to 0 1, these two cases are 0 1, so SR is 1 0. Next is Qn is 1 and Qn plus 1 is 1 for these two cases. So for that it is don't care 0 and for Qn 1 and Qn plus 1 0, for these two cases it is 0 1. So we can write 0 1. So we have drawn the conversion table also. Now our fifth step is to, using kmap, simplify the logic expression for excitation inputs of the given flip-flop. So now we have to use kmap to get the simplified logic expressions of the given flip-flop, that is the SR flip-flop. So we can draw the kmap for S and R. So there are 8 combinations. So we'll be drawing a 3-variable kmap. So there will be 8 cells. There are 8 combinations here. So there will be 8 cells. So we are drawing 3-variable kmap Q1 JK. 0 0 0 1 1 1 1 0, and this is 0 and 1. So correspondingly we can mark the entries corresponding to Q1 JK 0 0 0. This is the kmap for S. So it is 0 0 0 1, it is 0 0 1 0 1 0 1 1 1 1 0 0 don't care, 1 0 1 it is 0 1 1 0 don't care, and 1 1 1 it is 0. So now we can group it. So this is the grouping. These two ones can be grouped like this. So we will get, this corresponds to JK and this corresponds to JK bar, and this is Qn bar. So we can write the expression for S as, here J is common for the third and fourth column and the row is Qn bar. So S is J Qn bar. And now we can draw the kmap for R. So that will be this is Qn and this is J and K. Kmap for R. So we can mark the entries. So here we can group these two ones together. So here 1 and 1 is common in these two cells. That will be equal to K, and this is Qn. So we'll get the expression for R as K Qn. So we have got the expression for S as J Qn bar and R is K Qn. Now the sixth step, that is draw the circuit of the desired flip-flop using flip-flop conversion logic and the given flip-flop. So we have to draw the circuit of JK flip-flop using the flip-flop conversion logic that we got now and the given flip-flop, that is the SR flip-flop. So we can draw SR flip-flop. So this is the S input, this is the R input, and this is the clock pulse. I am giving it as a positive edge triggered clock. We can give it as negative edge triggered also, and these are the outputs Q and Q bar. Now we can draw the JK flip-flop using this SR flip-flop. Realize the JK flip-flop using this SR flip-flop. For that we have got the expressions for S and R using J and K like this. So S is equal to J Qn bar and R is equal to K Qn. So I can give an AND gate over here, so that here I can give the input J and this will be equal to Qn bar. Qn bar, and R is equal to KQN. So I can give another AND gate over here and give the K input over here, and also I can give Qn over here. So that S is equal to, we'll get S as JQN bar. That is the output of AND gate will be JQN bar, and R will be equal to KQN. So we have got a JK. So here the inputs are J, K and the clock pulse, and the outputs are Q and Q bar. So now we have realized the JK flip-flop using an SR flip-flop.